So in this work, we address the problem of causal inference for spatial data sets. So let's dive directly into the problem. Suppose that you have a variable y, which is an outcome of interest, a variable z that's an exposure variable, and that this data is obtained over space. And we are interested in estimating the effect of the exposure on outcome. Or more specifically, we want to know how the average outcome would change at a given location had the effect been assigned a value of z tilde and if it changes around that. So to give an example, outcome y could be income over different states of Germany, and the exposure variable age could be exposure variable z could be age over the different states of Germany, and we could be interested in understanding how age affects income in different locations. Now, what makes this problem non-trivial is the presence of unobserved confounding variables. For example, here we show unemployment, and we can see that it's very strongly correlated with age. And had unemployment been unobserved, then we might enter in a situation where the actual effect of exposure on outcome is zero, but we still see some covariance between z and y because of the unobserved confounding variable. So to address this problem, we make certain assumptions. We start with the conditional independence assumption, and then we further make the assumption that this expected value can be approximated by an affine function in the exposure at a given location S. With these assumptions, we get the following data model, but we can't really use this data model directly because it leads to some problems because of this nuisance function beta S. To illustrate that, we consider an example in two-dimensional space where this is the true effect, and this is the estimate we get when we use equation 2 directly. On the other hand, our proposed method gives something closer to the true effect. So our method depends on residuals. We define these two new variables, w and v, which we call residuals. And if we plug these in equation 2, then the nuisance function, which was creating problems in the previous slide, it gets eliminated. And the effect tau of s is directly identifiable from equation 3, given that we know w and v exactly. We can use any parametric model for tau of s. For example, in this case, we use the following parametric model. But the problem is that what we're missing here is that these residuals w and v, they're not known exactly. They are always estimated, and therefore we have an error in variables problem here. If we plug these two last equations back in equation 3, we get something like that, where we see that the delta S in blue is the unobserved random deviation that we need to cater for. So our method, we propose a robust formulation which basically provides robustness against the worst case deviation. A worst case random deviation, we don't know it, but we suppose that it lies in a set where each element, where the random deviation is bounded by some known quantity. So in this way, we get robustness against the unobserved random deviation. And moreover, equation 4 is a convex problem, and it can be solved using coordinate descent. So to illustrate it on a real data set, we consider the number of crimes data and the number of poor families data from the US Census Bureau Census Bureau statistics for the year of 2000, and try to see if there is a relationship, if there is an effect of the number of poor families in a state with the number of crimes in that state. And we see these results show that we estimate a positive effect, which is significant at 5% level, and it's consistent with some previous findings as well. So in short, we basically propose a strategy that provides a robust effect estimate, and it's robust against errors in variables. And you're welcome to our poster, which is poster number 80 at the Pacific Ballroom in the evening. Thank you.